Thank you for introducing me. So hi, good afternoon, I think. I'm Sam. I'm a final year master's student at Leiden University, and this year I did a 3-month visit to Monash University with Daniel and Teja Danilovic for my master research project, and I also saw some cute koalas. And today I'm going to talk about AGB stars. And on the left, you see an AGB star that has been observed by ALMA and its CO mission. And next to it, I put a simulated AGB CEO mission that I made in Phantom. And today I'm going to talk about how we came from this picture from Alma to this simulated image. So to start, let's have some context. So the AGB phase is the final phase that a star goes through, and in that phase, it experiences mass loss. And as you can see in this diagram, a lot of shocks happen. I don't know if you can see my cursor, but these shocks, these stellar pulsations happen, and that drives dust formation and eventually launches a dust-driven wind in the so-called circumstellar envelope. And that wind carries dust and particles and a lot of molecules, and we want to model that. And well, you get these nice spiral shapes and a bunch of different kind of shapes due to these AGB outflows. And as you can see in the gallery, there are a bunch of different kind of AGB outflows, and we don't know exactly why they are shaped like this and what their differences are. We think that this might have to do with binary interaction, so a binary companion that interacts and helps with forming these spirals and the wind. But we don't know how the chemistry actually influences these outflows and the other way around. So that's what we're going to try to model. And just some basic astrochemical modeling. So for example, take a reaction A plus B forms C. The rate of change is this equation. And if you include different reaction types, such as photodissociation, where a photon hits the molecule and splits it up, then the total range rate of change of the abundance, so the amount of C relative to hydrogen with radius, is actually an ODE that we can solve. And don't look at this equation, but the important thing is that this part here forms species and the other part destroys species. And with that, we can calculate abundances. And in 1D, we assume a spherically symmetrical CZ. And you can see that here the parent species, which have an initial abundance at the start of the model, they form an envelope and then eventually photodissociate. And then daughter species, they have the opportunity to form later. So they form from these parent molecules breaking up, and eventually everything is destroyed and it goes out into the ISM. And for example, this was for a carbon-rich star. And well, this is in 1D, so there's also no time evolution, and we wanted to do this in 3D. And for 3D modeling, we need to do some tracing. So we trace particles from a phantom model, thanks to Camille, and we get from that the coordinates, density, temperature, and extinction. And that looks like this. So you see that for each particle over each time step, we get all these parameters. And we use that as input for the 3D evolving chemical model. So that's what you see here is that the particles are being traced, and we can get the density and the CO abundance from that. And you see that the CO abundance evolves over time as the outflow goes out. And well, this is only for 15 particles, but we want to do this for all of the particles. And for that, a typical phantom HB wind model uses like 4 million particles and 1600 time steps. And the evolving model calculates those abundances of the species for each particle at each time step. So that totals to 6 billion calculations. And if we also multiply that by the amount of species, we get 3 trillion data entries. So that is quite a lot of processing and a lot of files, terabytes of data. So for that, we needed to do quite a lot of file management and also introduce some parallel workflows. So the pipeline that I designed does that by first going through all the particles. So we get the phantom model and we calculate column densities with Macquarie with ray tracing and get that into an analysis module that also gets the other parameters, so the coordinates, the density, and the temperature. And we organize that all into 10,000 batches. And that has the trace of every single particle organized into those batches. And then we submit 10,000 jobs. And why 10,000? That's actually the limit of the supercomputer that we used, the amount of jobs that you can submit. And then for every batch, it contains about 400 particles. And then in serial, we calculate the chemistry. So that's what's happening here. And we eventually convert that to one file of a batch with all the physics and the chemistry of every particle in that batch. So the parallelism comes from the 10,000 jobs, and then it's 400 particles in serial. And once we have that, we have every batch, but we want to organize it in dumps. So we get back the time steps, and therefore we need to scatter that batch across dumps. So the chemistry and physics of every particle is then organized by dump, and we do that with 10,000 jobs again. And then after that, we gather all those scatters organized by dump, so that eventually with 1,600 jobs for each time step, we get one file with physics and chemistry of every particle that exists in that dump. And this is the complete image, and it looks like a lot. But I'm happy to say that running this in total only takes about a week for a phantom model. And the phantom model that we used was a model from Owen Vermeulen from 2025. And it used a mass loss of 10 to the minus 7 solar mass per year, a velocity of 10 kilometers a second, and a binary separation of 9 AU. And what Owen did in his paper was only calculate the CO photo dissociation. So that's what you see in the slice here in X and Z. And that you have the CO here, the CO density. And the cool thing about our model is that we've got actually the first 3D chemical model of an AGB outflow that includes all the gas phase chemistry. And that looks like this. So you see that this is quite a bit different, and that's actually because there is more chemistry happening. So there's also CO, also an XZ, and you see that, for example, those contours are a little bit different because there is just more chemistry happening here. And the fun thing also is that we don't only do this with CO, but with a lot of molecules. So, for example, for all the parent species at 200 AU, you see a lot of structure happening throughout all these molecules. And it's also really nice to see that each molecule, we know each molecule behaves differently. And we really see that back here in these slices. But we also nicely see that most molecules, for example, here you see the temperature structure in XZ of this model. And you see that these shocks that are happening here are also followed by most of the molecules. So it's really nice that you can see that back. And what we can also, a nice showcase is that, for example, this parent, you see that it forms in these spirals, but also inside the outflow. And we know with a parent that it has an initial abundance, so it's going to be there, and it eventually photodissociates into these daughters. So that's a C2H in this case. But C2H doesn't have an initial abundance and only forms when the parent photodissociates. So you see here that it only forms in the outer outflow. which is exactly what we expected. So that's really nice. And also, we can see here a 1D representation, so it's 3D data, but we can organize the abundances into radius bins. And for every point here is the particle count of abundance at that radius that exists. And this is a pretty nice representation compared to 1D. And you see here that this line is the 1D model overplotted. And the median of the 3D data follows that pretty nicely. But you see in the point density, so all these points, that there are multiple pathways that the molecules take in the abundance profile, which is exactly what we think when we compare a symmetrical, smooth 1D outflow to a 3D outflow, that because it's not symmetric and because there are different things happening in this model with spirals and stuff, that there are multiple paths that it can take. So for example, also here, if you can see these lines here, these are what is happening in these spirals. So that's really nice that you can see that back. But yeah, in general, the 1D model and the 3D model compare pretty nicely. And well, I've shown you a bunch of molecules here, but the fun thing about this data set is that we can do this for 466 molecules, and that looks like this. So this is an XY slice of every single molecule that's included in this data set. So there is a lot to do with this data set. We can do so much with this. And well, to conclude, this was the first 3D chemical model of AGB outflows. And for the first time, it allows us to really investigate how the shape and properties of an outflow influence the chemistry and vice versa. And this pipeline is also suitable for basically any phantom HB wind model. So we use this one for now, but any model should be suitable to calculate the chemistry on. And what's in store is that we still want to do some radiative transfer modeling to convert this abundances into synthetic observations that we can compare to ALMA. And also, we can probably integrate the evolving model in a phantom analysis module, so you can basically calculate chemistry on the fly whilst you're calculating the phantom model. And we're also working on emulating chemical evolution. So there's a lot coming for this, but it's a really nice proof of concept that this model works and this pipeline works. So thank you for listening. And here's another cute koala picture.
Questions? You can just, I think the audio is very good. So just if you have a question, just ask.
Yeah.
Yeah.
I have a question. Hi, Sam. Nice work. I don't know if you have an answer to this question, so I don't mean to put you in an uncomfortable position. But you showed the difference between the CO abundance between Owen's plots and yours in the CO. And this morning you were still sleeping, sorry, but Camille showed. I mean, they defined CO as the most boring molecule in the AGB outflows because basically nothing happened in COs. And I think I know that you use CO as what you call parent species. So in the beginning of your chemical thing, you already have CO. And then it never interacts with anything until it photodissociates in the alpha, which is what Owen was already accounting for. So I'm a bit confused by why these two pictures are different if basically CO is already parent species and then it just photodissociates. So if you don't have an answer, it's no problem. But also the scale is different, like the...
I'll get into that. So I'll first talk about the scale of the image. Owen actually did NCO, so number density times CO, and this is the abundance. So if I also have one multiplied by number density, and then you basically get the same values. So that matches. And why this is different is because photodissociation is one of the many reaction types that can happen. And CO, in this case, we used a bunch of gas phase, like all of gas phase chemistry. So I don't know exactly which other reactions are that. That's something my supervisor knows better. But I know that because we also include those reactions that more is happening. And I think that's why it's different, and it also looks a bit different because it's the abundance compared to the number density.
Yeah, I think. Well, so hi, Sam, Owen here. About the same figure, I think it's mainly because we just treat dissociation differently. Because I use a dissociation rate from a table, whilst you use the one that is in your code, right?
Yeah.
So I think that's actually the main difference between these
okay, that could be.
I don't think CO dissociation depends that much on the full dissociation of other molecules happening in the outflow.
Yeah, okay. Yeah, that could very well be. But in general, we found that it overlaps pretty well. So in this case, it's just then I think a difference of how we plotted, rather than like a real physical difference.
That's terrifying. So are you saying that it's just a choice of the photodissociation parameter?
Well, so the way that I did dissociation, it also depends on the strength of the dissociation rate that you choose, and it also makes your envelope bigger or smaller. So it's also just a parameter that you can tweak to get a different size of your envelope. Look up the literature on this.
Yeah, so we used a big reaction network with a bunch of photodissociation rates. So I don't exactly know which values we use. But
Are you saying there's uncertainty in the rates? Is that the point?
no, I just don't know compared to his methods, what the difference would be.
Yes, we're taking all of this as like ground truth because we know nothing about chemistry, but chemists will tell you that these reactions come with massive uncertainties.
So you found the bugs in chemistry, basically.
Yeah, because they are taken
aware
from
of it.
observation. So there are a lot of uncertainties in that.
There any other questions?
I have one, if there's time. Thanks, Sam. I will always be happy to look at your plots, I think. You said it took you a week to run the whole pipeline in the end, right?
Yeah.
On how many cores?
So that's on 10,000 CPUs. So because it was embarrassingly parallel, sorry. So it was 10,000 cores. But I think that with this idea that we had with integrating the evolving model in the phantom analysis module, then that could be done differently, because I think that not every cluster has 10,000 jobs available.
Wait, you mean actually concurrently? 10,000?
Well, the whole point is that, as you said, it's embarrassingly parallel.
Yeah. So
there would no way of taking 10,000 jobs at once. No way. But it will easily take
no. So actually, the limit of how many jobs you can submit at once in this cluster is 2,400. So I basically did 2,400 times 4 or times 5, and the scheduler then plans that in. So it's not 10 once, but the most I've seen is like 3,000 running at once.
Yeah, I'm just trying to scale it to, regular person values, because we don't all have access to that sort of power.
I don't think anyone would claim that we have like amazing supercomputing in Australia.
Yeah, but yeah, the evolving model now with we didn't use all the reactions, but we used a lot of them, and it's about 4 minutes per particle for the entire time range. So it depends on how many particles you want to use, because we found out that you don't need to necessarily use all of them, but for plots like these, you do. But in general, like if you want to know some chemistry, you can use a subset of the particles, and then the runtime also is a bit lower.
So we need to move on. Let's thank Sam again.
Yes, thank you so much for listening.